So from this session we'll be starting with the instruction set and programming of 8085. So this will be the more practical based content of this syllabus. So we'll now learn the various instructions of the microprocessor that will relate with the architecture, the pin diagram of 8085 that we have studied. Some of the things were not clear, have not been clear so far, but with instructions, as we study these instructions, the things will be more clear and we'll be able to see how microprocessor basically executes programs. So as far as instructions are concerned, there are 74 instructions in 8085. So using 74 different instructions, we can basically be able to execute various types of programs in 8085. These instructions can be divided into 6 categories. These categories are data transfer group, secondly we have the arithmetic group, we have the logical group, we have the branching group, we have the stack group, and the machine control group. So as the name indicates themselves, in the data transfer group, these instructions will be basically dealing with the transfer or in the flow of the data between the memory and the microprocessor, between the registers and the microprocessor, direct transfer of data to the microprocessor, extra. So under this group we'll be actually studying 15 different types of instructions. Secondly, we have the arithmetic group. In the arithmetic group we have 20 different instructions. These are simple arithmetic operations like addition, subtraction, multiplication, and other types of arithmetic operations. Then you have the logical group that consists of 19 different instructions. So using the logical group, we'll be actually seeing again various types of instructions of 8085, and using these instructions we can basically perform logical operations like AND, or NOT, extra. Then we have the branching group, and under branching group we'll be seeing 8 different types of instructions that are actually these types of instructions will be used. So these types of instructions will be used in branching applications, like say for example calling a subroutine or jumping to a certain location. Some of these instructions we have already examples have already seen, like JZ, JNZ. Fine. Then we have the stack group of instructions. These are 6, and similarly machine control group of instructions, we have 6 different types of instructions. These types of stack group instructions will be used for operation of stack pointer, operation of subroutines, and similarly machine control group will be these are used in the control operation of the machines, status and control operation of the machines. So these are different instructions of 8085, different types of instructions in each types of in each group. We have a number of instructions, and they have been classified on the basis of the main type of behavior they execute, whether it's a data transfer, whether it's arithmetic operation or a logical operation, extra. So these instructions we'll be studying one by one. So before that we'll need to understand the formatting, the instruction format of the microprocessor. So first of all, the size of the instruction. We need to understand what will be the size of any instruction. So accordingly, the micro in 8085, you'll see a single byte instruction. The size of the instruction basically refers to number of bytes that the instruction will take takes in the memory. Fine. The memory that's actually interfaced with the 8085, how much of that's actually associated with 8085, how much byte of memory will the instruction basically occupy, will be accordingly we'll be able to decide the size of the instruction, and this will be actually useful for us to execute the programs. We will be able to exactly decide where to provide the data bytes while any program is being executed. For example, we have a single byte instruction. Say for example, in this case we have move a comma b. So an instruction on its own, since I said to you, the instruction in a microprocessor is defined through its opcode, and opcode will be a hexadecimal number. So say for example, this is just an example, this is not the exact opcode of move instruction. Say for example, I am saying 76H is the opcode of MOV. So this is a 8-bit of 76H basically refers to 8 bits of binary number. When we'll transform 76H, 76 hexadecimal number to binary, it's basically 8 bits of data. So 8 bit means 1 byte, so it's a single byte. This opcode is basically taking for every instruction that will be using, almost every instruction that will be using, the opcode will be a hexadecimal number, and it will be occupying 8 bits of data. That's a single byte in the memory location. So the instruction itself is taking up the single byte. Now associated with this is A and B. So what this instruction basically does is it basically moves the contents of B to A. B is a general purpose register, that's actually internal memory of the microprocessor. A is the accumulator, again a general purpose register. So this instruction will not occupy the contents that are actually stored in B. The contents that will be transferred to A will not be stored elsewhere in the memory. So this A and B here, they are not taking up any space in the memory. So only the opcode itself is taking a memory, and since it's equal to 1 byte, so this instruction is a single byte instruction. Secondly, we'll be seeing 2 byte instructions in 8085. For example, MVI A, 32. Fine. So what this instruction basically does is 32H is the data that's given to us, and that will be immediately transferred to the accumulator. So what happens in this case? Again, the opcode of MVI, it will be some hexadecimal number. Fine. And this hexadecimal number will take up 1 byte, while as accumulator, since it's an internal memory, and it's not actually, we are not storing in, we are not, the data is not actually present in the accumulator, we are transferring the data to accumulator. But this instruction, what it does, it immediately transfers the data byte that's provided here, that's 32H, to A. Now this 32H has to be actually located somewhere in the memory. So this 32H, since it's a single byte, again it's hexadecimal number, it will take up 8 bits of, it will be equal to 30, if we say about 32H, and we can basically represent this in terms of binary equivalent as 0 0 1 1 0 0 1 0. Fine. 0 0 1 1 0 0 1 0. So this is 32H, it takes up 8 bits of data, and this 8 bit of data is equal to 1 byte. So 1 byte is basically taken up by the opcode, 1 byte is taken up by the data that's actually being given, in this case immediately, with the instruction itself. And since this data has been provided there, this data had to be somewhere in the memory first, so it will be basically taking up a space in the memory, and therefore this totals up to a 2-byte instruction. So this type of instructions will be 2-byte instructions. Fine. We have single byte instruction, we have 2-byte instructions, we have 3-byte instructions. So these types of instructions will be taking up 3 bytes of data, 3 bytes of memory, 3 bytes of space in the memory. Fine. For example, LDA 3000H. Fine. So what this does is basically this type of instruction is used to load the register pair with this instruction basically loads the accumulator with the data that's actually located at this memory location. Fine. So this instruction, when we write this instruction, this basically means transfer load A with the data that's actually stored at this location. 3000 is not the data here, 3000 is the address. Fine. So again, LDA, it's an opcode, it will have an opcode, a single byte opcode. Fine, it will have a single byte opcode. Now this 3000H, it's not an 8-bit number, it will have a 16-bit binary equivalent. That means this will take up 16 bits of space in the memory location, that's actually equal to 2 bytes. So total it will take up 3 bytes of space in the memory location. The opcode will always be written in the memory location, the data will be stored in the memory location. So what happens, so why do we need to understand this? Say for example, we have the memory. These are addresses. Say for example, this is 3000. So before 3000 there would be something like 2FF. Fine. 2FFE. So these are the addresses to these memory locations. 2FFD, 2FFC. Fine. So these are hexadecimal numbers, all of them are hexadecimal numbers, and you understand the hexadecimal format. So these are the addresses to the memory locations. Now say for example, I am loading this instruction LDA here. This is the memory location here. Say for example, I am loading LDA here. I am writing LDA here. It will not be written like LDA, it will be written in its in which form it will be written in the form of of its opcode. Say for example its opcode is FF. Fine. So the microprocessor will understand that this is the opcode of some instruction. It will execute the instruction accordingly. Now what it will do is it will basically jump to which location? To location 3000H. Now when we are basically saying this is 2-byte instruction, since we can only store 8 bits of data here, that means least significant bit will be stored here, most significant bit will be stored at this memory location. So automatically the microprocessor will basically fetch the data sorry about this, it's not right. So automatically there will be some data here. Say for example here the data is 30H. So what the microprocessor will do is that it will basically be executing this instruction at, you'll be basically specifying the location of the start of the instruction. You have defined the instruction from 2FFC. Now at this location it will basically read that the first instruction, the first opcode that the microprocessor basically reads is the opcode. It will by default, it will not take it as a data, it will basically take it as a opcode. So it will understand this is an opcode. The first thing that it reads is an opcode, not a data. So accordingly it will debug it, decode it. Now it understands which instruction it is. Now it will find, it has to basically fetch the data from which location? From location 3000, and from this location it will basically take up the data and transfer that data to the accumulator. Now this data will be taken one at a time. For example, it will first take out data from memory location 3000. That will be it will be stored in temporary register, that is actually Z in this case. Then again it will take up the data again. From next time it will again read the data from the data bus, 8 bits of data, and take it up at take it to in another temporary register, that will be W. So in this way it has to basically read this data in 2 goes, rather than this address can be read in it has the microprocessor basically process only 8 bits of data at one time. So this address, a 16-bit address, will not be executed in a single go. It needs to be executed, it needs to be run twice to basically fetch the data. First the least significant bit of the address will be loaded, and then the most significant bit of the address will be loaded, or it's probably vice reverse. I'm not sure about that right now. Anyways, so it will be basically reading it will be reading 8 bits of data. So 16 bits of data will be read twice, and the data is actually only 8 bits, but the address location is 16 bits. So the microprocessor needs to fetch the address accordingly, and since 16-bit cannot be read through the data bus single way on a single go, because the data bus only supports 8 bits of data transfer, so this has to be done twice. Fine. So in this way we'll be able to transfer the data. So what I actually wanted to tell is now say for example leave this instruction. Let's go back to instruction number 2 that we defined. 2 bytes of instruction, MVI A32H. Fine. So if you are basically writing a program at any memory location, so you need to first of all see how many bytes will it occupy in the memory space. Accordingly then you can write the opcode at this particular location. A program will consist of a number of instructions. Say for example you are first executing MVI then you're executing, say for example you're first doing MVI A32H, then you're moving this data to B, fine. Then you can again move this data back to somewhere else, or you can add this data. So each of these opcodes needs to be written on the memory locations. So you need to understand whether this is a single byte instruction, so that I can put the opcode at this location, fine. Since in this case this first instruction is a 2-byte instruction, so I am putting the opcode here. The next memory location will basically be utilized by the utilized for execution of this data. Then I can write move at this particular location, fine. So now I know move is only a single byte instruction, so it will be executed at only one memory space. In the next memory space I can again write some another opcode, that's for, say for example, for add, fine. So in this way you will be able to define how much space is required. Accordingly you will place the opcode here and then here or then here, fine. You need to now understand that if it is a single byte instruction, you'll put it here. If it's a 2-byte instruction, this space you cannot utilize this space, then you have to put it here, fine. If it's a 3-byte instruction, you cannot utilize both these two spaces. You will have to write at the third memory location after this opcode is being executed. So you will define the opcodes at memory locations. So you can only define it once you know basically how many bytes of data it will take. You will have to put the opcodes at certain addresses. You need to understand how much byte this instruction will take. Accordingly you will be defining your program, fine. So this is why we need to understand whether a instruction is single byte, 2 bytes or 3 bytes, fine. So once we'll do the programming, it will again become once we'll start with the programming, we'll be able to clearly see it, how we can execute different types of instructions and where we have to place the instructions according to how much bytes of space they will take in the memory. So this was one thing you have to note about the instructions, the size of the instructions. B, you will have to note the addressing modes. So what is addressing mode? It's basically the method of identifying the operand of an instruction. Method of identifying the operands of an instruction. Say for example, we have done these examples just right now. So this MVI here is your instruction, A and 32 is your operand here. What is these operands? What type of operands these are? We can identify them through the addressing modes, and 8085 basically supports 5 types of addressing modes. The first one is register addressing mode. So in this case the operands are in a general purpose register. For example, that we have simply done here, move A comma B. Here the operands that are actually associated with this instruction, that's A and B, these are general purpose registers of the microprocessor, and these are the operands in this case, fine. And most of the times, usually such instructions are single byte. Second is direct addressing mode. So in this case, the operand is basically the address of the memory location. Address is directly provided with the instruction. For example, like we have simply done right now, LDA 3000H. So in this case, LDA is the instruction, whereas 3000H is your address of the memory location. It is not the data, it is the address of the memory location. It has been directly mentioned as the operand in this case. Therefore the name direct addressing mode. Most of the times they are 3 byte mostly, can be 2 byte as well. Fine. So we'll also see those instructions that are actually 2 byte, like in case of IO operations. Say for example, you have an instruction in OFH. Fine. So you will understand that this is a 1 byte data here. This is not data, this is a memory location. The IO interface is basically done through 8 bytes of addresses rather than 16 byte of addresses. Then you have the register indirect addressing mode. So in this case, what is the address of the operand is basically not provided directly. Address of the memory location is not provided directly, but address is basically address is fetched from a register pair. For example, we have LDAXB. Fine. So this basically loads the accumulator with the contents of the address location that are actually given in the register pair. So that means when I write B here LD but with an LDX, it means basically this is a register pair, and we have defined B and C can be combined to form a register pair. So B and C will not be carrying, that register pair will not be carrying the data, that will be carrying the address of the memory location, and that has to be basically loaded in the accumulator using this instruction. This is what this instruction does, but we are concerned with what basically this operand here is. This operand is referring to an address that's actually stored in this register pair. Fine. It is not referring to data. Fourth, we have immediate addressing mode. So in this case, basically the operand is immediately available. For example, MVI 30 A comma 32H. So this basically transfers 32H to A. Fine. So 32H here is not memory, is not address of memory, it is the data itself. So the data has been immediately given with the instruction. Fine. So you can have MVI, you can have ADI, different types of instructions in case of subtraction, LXI, extra. So we can even have LXI B comma 3050H. So this instruction what basically does is it loads the register pair with the data. This data here, this is not address here. So what it does is it will basically transfer 30 to B and 50 to C. Fine. So most it's like this, or it can be 50 to B and 30 to C, but most likely it is like this. So the most significant bit goes to the register pair B, and the least significant bit goes to register C. So LXI instruction basically means load the register pair with the data that's being immediately given. Fine. So this MVI A32H is a 2-byte instruction, because MVI will take 1 byte, 32H will take 1 byte. While as this LXI will take 1 byte, 30 will take second byte, 50 will take another byte. So 3050 is a 2-byte instruction. So this is total 3-byte instruction. So again, immediate addressing mode can be a 2-byte or a 3-byte instruction. In this case, the data has been immediately given as the operand. The address is not given. Fifth, we have implied addressing mode. So these things need to be made clear. What instruction is following immediate addressing mode, what is following indirect addressing mode, what is following direct addressing mode. Fine. In direct addressing mode, the address is directly given. In indirect addressing mode, the address has been given, but that address has been stored in some register pair. That register pair has been given to us as an operand. In immediate addressing mode, there is no address. Simply the data has been given, and that has to be immediately loaded into the whatever is the most likely the accumulator. In this case, address of operand is implied. Fine. So for example, we have an instruction XCHG. We simply write this instruction. We do not write anything else with it. This is an instruction that actually what it does is it will transfer the contents of register pair HL to DE. Fine. So we do not, it can be actually a two-way process. It can be between HL and DE, or DE to HL. Fine. So exchange, basically it is an exchange. HL will be transferred to D and D will be transferred to HL. This instruction is simply written like this, XCHG. We do not specify anything else with this. So what is the operand here? That's actually implied, because the instruction actually knows what it has to do. So that is not written here in any fashion. It is simply implied. Similarly, there is an instruction HLT. Again, the microprocessor will understand what HLT means. There is an instruction PCHL. So again, the instruction is only given. The operand is implied. Operand is basically HL and program counter in this case. So these are two things that we have studied about instructions today. One is whether the size of the instruction, whether it will be a single byte, a 2-byte, or a 3-byte instruction. Accordingly, we can define the opcodes and place them at certain memory locations. And secondly, we have defined the addressing modes of the 8085 microprocessor, whether it's a register addressing mode, it's a implied addressing mode, it's a direct addressing mode, indirect addressing mode, or immediate addressing mode. You need to identify the instruction type and their addressing mode, so that we are able to basically clear whether what type of instruction it basically does. Fine. You need to be able to understand difference between LDA 3000 and LXI B3000H. Fine. So in this case 3000H is not the data, it is the address of the memory location from which data is to be collected. In this case, this is the data itself. This is not the address of any location. This is the data itself that needs to be transferred to BC register pair. So that's all for today. In the next session, we'll be studying the macro RTL and the micro RTL of various instructions of 8085.